This standard model is simultaneously the coolest thing in the world and the most frustrating thing because it works so well. And we know for a fact that it is incomplete. Thank you very much. Thanks very much. I'm extremely honored and humbled to be here, and it's a privilege to be able to be here at the Royal Institution, home of so many fantastic, talks and pieces of information that I've heard disseminated. Public communication of science. It's just it is an institution, given its name, that's appropriate. And I am going to take you through a kind of a thought process that I had a few months ago. And it all culminated in this title you see up here, which is a little bit crazy and audacious, I admit, right off the bat. A Big Bang machine on the moon. What in the world does that mean? So I hope that some of you at least came to the talk with that in your mind. But to set the stage a little bit before we get to the Big Bang machine on the moon, I grew up in southern Utah, and this is the home of red rocks and hot August nights and very clear skies, and these are perfect conditions for stargazing. And I remember one time when I was a little kid, a friend and I had biked out of town to get away from the lights of the town to look at the stars. And we were sitting on some hot, flat rock, probably eating gummy worms or something like that. And I remember we were too young to have telescopes, but I was kind of a library guy, so I wanted to show off to my friend. And I'm like, ooh, check it out! Look at that star there, Vega. It's 140 trillion miles away. I'd really read my book. 140 trillion miles away. The light that's been traveling from that star to get to us has been traveling for something like 25 years. Isn't it amazing how big the universe is, how large everything is? 140 trillion miles. And my friend says, no, it's not that far. And I was like, I didn't know what he meant. And I'm like, well, okay, maybe it's not exactly 140 trillion miles, but scientists are really good at these estimates, so maybe it's like 130 or something like that. And he's like, no, it's about a mile away. And I was like scratching my head, a mile? Well, what do you mean by a mile? Well, my dad says it's a mile away. And finally I lost it. I'm like, what are you talking about, man? Think about it. If that star was a mile away, we biked 5 miles out of town to get here. If that star was 1 mile away, it would be in a totally different place in the sky here than when we were back in town. And I drew him a little triangle, just on the rock there with another rock just to show him. And like, look, and he's like, but I don't believe you. And I said, believe has nothing to do with it. We can test it. And so we did that. We kept track of the star as we got on our bikes and went back back into town, and we were back all the time keeping track of the star. Go back, and we get back into town, and I go, look, it's basically in exactly the same spot. It has to be more than a mile away. And then my friend's like, but what am I going to tell my dad? And I'm like, you don't have to tell him anything. You can do the same experiment with him. And so apparently I never was able to rid myself of the love of, looking at challenges and problems that are there to be solved and then coming up with some kind of experiment to design them, to test them. But the questions that I ask now as an adult are a little bit more complicated than whether the stars are a mile away or 140 trillion miles away. The questions that I answer now, that I try to address now, are things like this. What is 95% of the universe made of? Why is gravity so crazily weak compared to the other forces of nature? What really happened just after the moment of the Big Bang? Do we live in a multiverse? And that last one is not entirely crazy. It's actually kind of an interesting story. So now not just the questions have gotten bigger, but the experiments that I do that I participate in to try to answer them have gotten a lot bigger too. So now I work on the ATLAS experiment, as Simon mentioned. ATLAS is one of the 2 big experiments at the Large Hadron Collider at CERN. And so this is actually, I'll show another photo of it later, but it's basically 6 stories high and 40 meters long. And it's a place where we collect debris from proton collisions. And for those of you, just to remind you of what the LHC is, it kind of looks like this. If you're in the tunnel, it looks more or less like this. And the LHC is a 27-kilometer circular tunnel on the border of France and Switzerland, buried 100 meters underground. And this is what it would look like if it were around London. And I was just told, in fact, that the 27 kilometers more or less is the, what is it, the central line or something like that? Or the yellow line? The circle line, yeah. So basically it's like the circle line, but put that in the border of France and Switzerland. Yeah, so this is, I like this because you could get from Mayfair all the way up to Stoke Newington really quickly. It looks, yeah, so it's a 27-kilometer circular tunnel on the border of France and Switzerland, buried 100 meters underground. And in this tunnel, we use superconducting magnets that are colder than outer space to accelerate protons to almost the speed of light. And so you're going to be a proton here in a second. If you follow this animation, great, you're a proton. And now you can pick which one of the quarks you are. Are you red or you blue? And eventually, we accelerate these almost the speed of light, and then we slam them into each other millions of times a second. And we collect the debris of these collisions to look for new, undiscovered fundamental particles. Its design and construction took decades of work by thousands of people from around the world. And so that's what it looks like when a particle collision happens. I'll let this animation finish here. But then the place where the particle collision happens, you better put a gigantic detector because quantum field theory magic is going to happen. And so by big, I mean this. This is Atlas. This is hopefully a photo you've seen before. 6 stories high, 40 meters long. There's some lucky guy that got to stand there, right as they were bringing the electromagnetic calorimeter in. Hopefully, he wasn't standing there when they brought it all the way in. It would be a very sad story. But these are the types of experiments that I use now to try to answer these much bigger questions. Excuse me. And we're going to go a little bit into the details of what we're actually doing with these types of with these experiments, and why we need to go to bigger colliders, and why we've always had to do this in the past. And if this sounds complicated, it's not so bad, because really, at the heart of it, everything we're doing at this gigantic experiment, the biggest science experiment ever mounted, comes down to an extremely simple question: how small can I cut anything? How about a bagel? So I'm an adopted New Yorker. I did my PhD at NYU. I take a bagel. You guys take, a hot cross bun or something like that. So cut it in half. Cut the half in half. Keep going. How far can you go? Get to a molecule, right? You can cut a molecule. Yeah, you've got atoms there. They're held together. Can you cut an atom? Yes, the 20th century told us very clearly that we can cut an atom. There's a proton, and there's like a nucleus and some electrons going around. So can you cut an electron? As far as we know, the answer now is no. An electron is a point particle. It has no spatial extent, no volume. Can you cut a proton, though, the other part of the atom? As far as we know, yes. There's stuff inside a proton. There's 3 quarks and some other thing called gluons roiling about inside the proton. Can you cut a quark? As far as we can tell, no. But that's just based upon the precision of our measurement and our measurement device now that tells us that we can't go any farther than that. So, as it turns out, as you can tell, when you ask that seemingly very simple question, how small can I cut anything, you're secretly asking a very deep question. What was holding anything together to begin with? And once you do that, the history of the 20th century was a phenomenal success for science, because this was really just people asking this question over and over, and finally getting this interesting interplay between theory and experiment throughout the 20th century led to essentially a list of the basic constituents of nature that we know exist and the ways that they interact. And this is what we codify this in something we call the Standard Model, capital S, capital M. It's honestly one of the most impressive intellectual achievements of humankind, because it's more or less this kind of mathematical theory that you can write. You can start with some basic math stuff. You crank through the math, and it makes these precise predictions as to what you should see if you go out and perform an experiment, like a particle collision experiment. And it's worked so well throughout the 20th century that it's almost like it's gobsmacking how amazingly well it works. And some of you may have heard. Who here has heard of the Higgs boson? Yeah, okay, great. That's good. So I don't have to do too much work on the Higgs boson. But I am going to give you a little bit of an insight as to why the Higgs is it's both a fantastic success for me and my colleagues. Yay, we discovered the Higgs boson, hooray. And the Higgs boson was the last remaining piece of the Standard Model, this linchpin of the Standard Model that goes in the middle there. And so, of course, it was the science discovery of the year in 2012, and the two white males won the Nobel Prize. What else is new? And for this, and so the last remaining piece of the Standard Model be plugged in, and it was the last guaranteed discovery that we had, because it was the last thing that the Standard Model predicted. This standard model is simultaneously the coolest thing in the world and the most frustrating thing because it works so well. And we know for a fact that it is incomplete. We know for a fact that as amazingly well as it works, as so well as it predicts the mass of the W and Z bosons, whatever those are, as well as it does this thing, we know for a fact that it's incomplete for some gigantically, catastrophically bad reasons. Number one, it doesn't contain gravity. And I just demonstrated that gravity exists. So this is a bad thing for particle physics. And we know that the standard model, as precisely well as it does for the elementary constituents of nature that we know exist, we know that it cannot be the full picture of nature. We know that there's other things that have to somehow add into that. So if we had a theory that had the standard model and included dark matter and gravity, a bunch of other things that I'm going to touch upon here in a moment, we would have a better description. We would have the real answers to all the biggest open questions, the ones that I was listing on that second slide there. And so the way we go to look for, how do we go to look for answers to these open questions is that we have to go to different experiments to try to find where these new particles are. So we got to the end, and this Higgs boson was the last thing we discovered. Fantastic, Nobel Prize winning discovery. But if we're looking for these new particles that may help us, that might be extensions of this standard model, we have to go to different experiments. And by different experiments, I mean bigger experiments. And by bigger, that has, why do I say we have to go to bigger experiments? Is because it all comes down to Einstein. So E equals mc squared, everybody knows E equals mc squared. What does this actually mean? At the particle level, what this means is that there's an equivalence between energy and mass. And mass is just a number put there by nature. So if I'm a particle, I have an individual mass m, and it's just, that's what it is. Nature picks that number. So this is the part that nature can control. However, E is the part that we can control as experimentalists. If we work hard enough, we can design an experiment that has enough, we put enough juice into it, put enough E into it so that we can get an E up high enough to hopefully discover the particle with a mass m. So if nature has a particle with a mass m that's right up here, and we as a species have only ever made an experiment that goes up to here with E, we'll never discover it. We'll never be able to study it. We'll never do anything. We'll never know that it exists. So that's why we have to go to bigger colliders. And the bigger the collider, the higher the energy, and the more access you have to particles that may exist that answer some of the biggest open questions that we look for right now. And so a couple times in the rest of the talk, you'll see this kind of thing that says TeV, trillion electron volts. Don't worry too much about it. It's just like a measure that we use for energy and mass for particles and the energy we put into it. So more is better. And more is better in a very kind of key way, too, because when we go to high energies, you might ask the question, it's like, well, why is it so hard to look for these particles? Why do we have to go to such gigantically high energies, bigger experiments and things like that to look for these particles that may explain these things? Why can't we do something lower energy? It's primarily because the universe as it stands right now is really, really boring. And it's really, really cold. So this is the history of the universe going backwards. And this is actually the current slice of the universe right now. If you take the average temperature of the universe just right now, stick a thermometer out in outer space, it's going to be very low. The average temperature of the universe is extremely low right now. And so this is today, 14 billion years after the moment of the Big Bang. This must be the 1950s, because that's a nuclear family there. Oh, I'm using the laser pointer. This must be the 1950s, because that's a nuclear family there. But if you then just logically, and we know that when you look out in space, you see all the stars and the galaxies moving far apart from each other, farther and farther away. So if you just run time backwards, at some point they all had to be packed down into some tiny, hot, dense, insanely energetic point. And so that's, of course, you go back, run the clock backwards, and eventually get back to the moment of the Big Bang. And that's the highest energy ever. And so what we're doing when we go to high energies is that we're at this collider experiments. So we take these protons, in this 27-kilometer tunnel, we accelerate them almost at the speed of light, faster and faster and faster, higher and higher energies. That gets us up to a moment of the universe's history when the average energy was really, really high. And this was the point at which some of these particles we're looking for that could help explain these open questions may have existed in abundance. And that's why they don't exist now, because they died out, and then the universe expanded too much, and that wasn't important for them to stay stable anymore. And so we have to briefly recreate the conditions of the universe as they were a fraction of a second after the Big Bang. And the Large Hadron Collider gets us up to about right here. So what we do is we go back in time. We can get back to the 2 minutes and 1 second, and eventually we go. We're not satisfied with just a fraction of a second after the Big Bang. We want to know what happened a fraction of a second after the Big Bang. So this is all that we're doing in particle physics, and the Large Hadron Collider gets us to that point. But as I said, the standard model is incomplete. We know there have to be other things out there, and I'm going to mention some of the ones that I mentioned on that introductory slide. But so we can get back to a very, very short time period just after the Big Bang, but we want to go back farther because that's where the discovery could be. But part of you should actually still be saying, I totally don't understand what you're talking about. You're just saying that we're make particles. I mean, what does it mean when you collide two protons together? Is there, and you're looking for dark matter, or you're looking for a Higgs boson? I mean, was the Higgs boson like hidden inside the proton? Are you filled with Higgs bosons right now? You're not. There are no Higgs bosons in this room right now. So where are we getting these from? How is it possible for us to take two protons and slam them together and hopefully come up with a new particle that will help explain these open questions, and that may have only existed in abundance just a fraction of a second of the Big Bang? It's because we need to talk a little bit about how we actually look for new particles and what we mean by this. So there's not just high energy. High energy is not the only thing you need to discover a new particle, because as some of you may know, we say we use the highest energy ever, used in a collider experiment for these at the LHC, at the Large Hadron Collider. But there are much more energetic things that happen in the universe all the time. So in the upper atmosphere, at the LHC, we use this thing called 13 TeV, trillion electron volts. In the upper atmosphere, you have cosmic ray muons coming in all the time that hit particles in the upper atmosphere that are something like PeV. But there's only a few of those, and they're spread out all over the atmosphere. What we need statistics. We need a very, very large number of collisions to build up enough enough collision events, so that we can determine whether we've seen something new or we've seen something that's not new. So it's even that sounds like a little bit hard. You get a bunch of collisions and you look for a bump. It's actually really, really simple. How you discover a new particle is a simple three-step process. You accelerate protons to high energy and collide them millions of times per second. No big deal. Collect lots of data. And then you look for a deviation from what you were expecting. And so this is more or less a real-time discovery of the Higgs boson. So what we did to make this plot is that we collected data, we collided protons, millions of times a second for months and months and months, and then we picked out of those collisions. Overwhelmingly, these collision events are boring. We don't care about them, and so we toss most of them out because they're all this. You saw that earlier, that second slide that I showed was sort of the red fuzz coming out of that thing. That red fuzz in the middle there happens all the time, and it's boring in the sense that we know it. We know it very well. So we're looking for the events that have these unique features, those yellow things that were sticking out the side, going bing, and those are the ones we look for. And so for example, to discover the Higgs boson, we picked through all these events and found the ones, tagged the ones that were really interesting looking, and then we did this thing where we make an invariant mass out of them. Don't worry about it, but eventually what you end up with is this type of plot where you can see there's a tiny, tiny little bump there. You can see right around 120. It's going again. 125 in this plot on the x-axis here, and you've seen it a couple times now. Anyway, so that's enough. That means that we've taken enough data. That's enough for us to say this is a new particle, rather than just a fluctuation of the background. So that's the very, very simple way that we look for new particles. But again, to get back to the real heart of the matter, which I'm not going to belabor the point, but you really need to get, it's important to understand this so that we can understand why I want to build a particle collider around the circumference of the moon. What's really going on inside of a proton collision? Once again, back to that question, is there a Higgs boson secretly hidden inside the proton? Or maybe there's some dark matter in there. If we hit it hard enough, it'll knock the dark matter off. That's not what's happening. What happens with a proton collision is actually the two protons get close enough so that they can feel each other with a certain force. Because that question that we asked earlier, when you're asking, how small can I cut anything? You're secretly asking, what was holding anything together to begin with? And the thing that holds things together at the particle level are forces. But at the particle level, forces are mediated by other types of particles. It's like a force exchange. So it's a little bit strange for us, humans. We're big, bulky humans that evolved in this, on the surface of the Earth in this certain energy range, and we can't really intuitively understand the quantum world. But the quantum world is a bit odd. So, but one way you can, as an analogy, you can do it is, for example, you can get a sense of it is, you imagine you and your friend were on an ice skating rink. Okay, and you're both standing right in front of each other. One of you has a gigantic ball, like a big rock or something like that, and you throw the rock to your friend. As you throw the rock, it's really heavy, so you're going to slide backwards, right? And as your friend catches it, she's going to slide backwards as well. So in a sense, we have just exchanged a force-carrying particle. That's the way particles interact. But particle collisions are weird compared to what we think of as, collisions in our everyday life, because if you were actually particles in the quantum world, you and your friend actually have another option for when you throw the rock. You can not just throw the rock to each other. The two of you could actually smack together and become the rock. Perhaps let's use a different analogy. Particle collisions are not like car collisions. We like them to think so. We like to think of that in a way, but they're not like car collisions. They have different rules. When two particles collide at almost the speed of light, the quantum world takes over. And in the quantum world, two particles can actually cease to exist, and a new particle can be created in their place that lives for a tiny fraction of a second before then splitting into other particles that hit our detector. Imagine a car collision where the two cars vanish upon impact. A bicycle appears in their place, and then the bicycle explodes into two skateboards that hit our detector. Hopefully not literally, but this is the sort of thing this is a bit of a weirdness that happens at the quantum level. So the way that's possible for that to happen is that go back to your high school physics. I hope I'm not going to scare anybody off by saying go back to your high school physics. Go back to your high school physics. What does physics really care about? Physics doesn't care about the names of things. It doesn't care that this is called an electron and this is called a positron. We care about that for car collisions. Is Mary okay? Is Jack okay? But particle collisions, they don't care about that. Physics cares about conserved quantities. I hope I haven't made anybody fall asleep just by saying those words. Physics cares about conserved quantities because you think about what it is that the conservation of energy, conservation of momentum, conservation of charge, and some more arcane ones, conservation of spin. These are the things that particle physics cares about. So as long as I conserve these things before and after a collision, I'm all good. So here, for example, this is a diagram. I hope I haven't scared anybody off with a diagram. This is a Feynman diagram. Maybe Richard Feynman. But on the left-hand side, you have two quarks coming out of the proton in one of our collisions. Two quarks. At some point, they're far apart in space. They get closer and closer together, and at some point, they annihilate. They cease to exist, and then a Z boson appears in their place. And then the Z boson lives for something like 10 to the minus 12 seconds, basically nothing, and then it splits into two muons. That's crazy. You started with two quarks and ended up with two muons. How is that even possible? It would never happen in our everyday car collision world. But it's possible in the quantum world because as long as you have conserved all of these, you've satisfied all these conservation laws, it's totally possible to do that. And so this is what we do to look for new particles, because the thing we care about is that middle part, the Z thing. What is that Z? The Z is the force-carrying particle of something we call the electroweak force. And that's one of the four fundamental forces of nature. But the middle part doesn't have to be something that we've already discovered. It can be a new thing. I can hypothesize something new to put in there, and as long as it satisfies all of the properties that I need, all the conservation laws, I can put whatever I want there, and then I can go out and search for evidence of it coming, of the particles coming out the other side. So that's really what we do in a nutshell in the bread and butter. And so. But if, for example, it goes back to the E equals mc squared thing. If the thing in the middle, something I'm looking for, has a mass m that is way, way high, much higher than my experiment can get to be able to discover it, I need to give the introductory particles a lot more energy, and so I have to go to a bigger machine. So this is the point we find ourselves in, and this is where I'm finally getting to. That was all introductory boring stuff. I hope you can get, you're still with me after the introductory boring stuff, because we're now getting to the actual crux of the matter, which is that we're kind of at a bizarre, weird, a tough point right now in particle physics. We're scratching our heads really, really hard because we don't really know where to look now for the new particles. And that's frustrating because the 20th century was really good There's so many suggestive hints throughout the 20th century. It's like, oh, you should, we see this thing in our equations, and this other observation in a different experiment. You should look in this place. Whoa, there it was. Amazing. Oh, this suggests this thing. Whoa, you should do that experiment. This kept happening over and over. And the last thing was this Higgs boson discovery. And we discovered it. Hooray! Nobel Prize. Not for me, but Pat, my colleagues, 6,000 people discovered the Higgs boson. If one person ever tells you they discovered the Higgs boson, they're probably looking for a job. So, the point at which we discovered the Higgs boson was that the LHC had a lower energy than what we possibly could get with the 27-kilometer tunnel. It was designed to go up to a certain E to help find particles with mass m. But there was a problem at the beginning part when it was turned on, so we decided to operate at a kind of a lower energy. That was enough to discover the Higgs boson. Hooray! But it was not enough. It was not as high as we could possibly go. So 2015 was a watershed moment for humanity, because we finally achieved 13 trillion electron volts, TeV. This is the highest collision energy that any particle collider had ever used. And so June 3rd, we were waiting for the first collisions here. We were sitting in the Atlas control room, looking like Norse gods or something like that. And then, so we finally saw the first collisions popping off the detector at 13 TeV, and it was a really, it was a great moment. And we had no idea what we were going to find in this data. We had discovered the Higgs, made this jump, almost like this jump into the unknown, almost like a shot into the dark, into outer space. We had no idea what we were going to find. And then after 3 years of analyzing all this data, we haven't yet found anything. And that is, it's both good and bad, to be honest. It's bad because it's like, oh no, there's no discovery, blah, blah, blah. But it's also good because particle physicists are not really, we're not really like, I'll be candid about it. The Higgs boson discovery is great, and I love the Higgs, and we study it to death, and it's one of the things that we'll be studying for decades because it's a very, very unique particle amongst all the particles that we know of. But it's also kind of bad because it sort of telegraphs to the rest of the world that our job as particle physicists is to make discoveries. That is not our job. Our job as particle physicists is to map out all the possible territory where new discoveries could be waiting. So we're more like cartographers than we are particle hunters. We're more like map makers. And so it's absolutely a success anytime you do, and we produce hundreds of papers each year, analyses of our data, different subsets of our data looking for new particles. And each one of those, I would love for there to be some kind of breathless pop-sci article in Gadget or something. It's like, yes, LHC rules out one more little place where a particle could be. That's great. That took decades of work and a bunch of dedicated team. That's awesome for me, but we're not doing so well at messaging, it seems. But the key, though, with the fact that we haven't found anything yet, is that we kind of expected to find something in this energy range. And that kind of expected is going to be most key here. Because the kind of expected, the suggestive hints, this is the thing that I mentioned, we're running out of those. We have always, throughout the entire 20th century, had really good hints as to where to find the new particle. The Higgs boson, prior to this discovery, there were a lot of suggestive hints that it should be in that range, and there it was. That was really nice. And in the past, different particles, like, oh, you've got 2 different copies of this thing. There might be a third one, and then there was a third version of a type of lepton. This kept happening. But we're running out of these suggestive hints, but we still have the catastrophic open questions. And they're not just small, I use the word catastrophic, maybe it's dramatic, but they're not just small problems, they're big problems. One of them, I'll give you a couple of examples, and they're related. One of them has to do with dark matter. So dark matter, as you may have heard, is this thing that we know exists, but we've never been able to find exactly what it is. And it comes from very key observations that are totally repeatable over and over and over. So take your favorite Hubble photograph. I hope everybody loves Hubble photographs. I do. Take your favorite spiral galaxy and count up all the stuff you can see. Okay, all the stars and things that you can see. And astronomers are really good at telling exactly what's inside these stars based upon the lights coming out of them. So you can basically get a sense of how much mass, how much matter is in this galaxy, right? Based on what you can see. Okay, that's great because then you can take that number you just calculated by counting up all the stuff you can see, this matter, the mass of this galaxy, and you can put it into the equation that comes from gravity. The thing is spinning, right? The spiral galaxy is spinning due to gravity, and we know how gravity works really, really well. So you take this equation out of your favorite textbook, you put how much mass is in there, and it tells you how fast the star should be moving, should be spinning, as a function of how far away from the center it is. It's great. You just get that prediction. And then you go out and observe it. It's totally off from the prediction. And it's not just a little bit off, it's way off. And you think, okay, maybe this is just that one galaxy, maybe that's that's a kind of a one-off. No, it's happening in basically all of them. This was repeated over and over and demonstrated that this is a big, big problem. So one of two things is wrong here. Either gravity is wrong, it's probably not likely, or there's more stuff there than what you can see with your eyes. And if it's not light, if it's not luminous, if it doesn't interact with photons, the force-carrying particle of electromagnetism, then it's dark. So this is dark matter. So this is where there are other empirical observations that demonstrate that dark matter exists, but we still haven't found what its particle is. We've never been able to find exactly what it is. And there's different ways that we look for this in different mind-based experiments, and at the LHC we can look for it as well. And typically what we look for at the LHC is what we're good at the LHC is not so much the dark matter particle itself, but the force that might connect the dark matter with our world. Because if you have dark matter going through you all the time, and you have about 1 billion particles of dark matter coursing through your body every second, and you've never felt them, they've never interacted with you, that means that dark matter doesn't like to interact with regular matter very much at all, if at all. But if it does interact, it would have to interact with some new force. We know 4 forces. There could be other ones, but maybe their force-carrying particle was only important just a fraction of a second after the Big Bang. Then the universe expanded too much, and that force wasn't important anymore. And therefore, dark matter was left cold, aimless, and alone. One way we could try to detect this, or we could try to demonstrate this, is to look for this gigantic, high-mass force-carrying particle at particle colliders like the LHC, and that's what we do. The other thing that I want to mention about these gigantic catastrophes in terms of these suggestive hints as to where the new particles could be living has to do with the Higgs boson. So Higgs boson, Nobel Prize, hooray. The Higgs boson is a bizarro particle. Because the Standard Model predicts its existence. It said, yes, should be something called the Higgs boson, and it should exist. It's some particle, it does this thing, it helps give all these other particles their masses in a certain way with its Higgs field, blah, blah, blah. But it's really frustrating because it doesn't tell us exactly what its mass should be. And if you go back to the whole argument that I've been making, E equals mc squared, if we don't know where to go to find its mass, why should we assume it's going to be within the range of one of our particle colliders? Maybe it's something gigantically high. But it wasn't. We found it right around the corner. I said there were some other kind of oblique suggestive hints that we should find that Higgs around the corner, but those are more or less kind of circumstantial. Turns out they were good. They were good hints. But there's nothing really in principle to prevent the Higgs boson mass from being something gigantically high. And you don't need to know the details about it, but just I put it graphically here. The Higgs boson mass should totally just roll down this hill and be something gigantically huge. There's nothing to prevent it from doing that, except if you postulate this extra symmetry of nature. Don't worry too much about it. This symmetry of nature called supersymmetry. Some of you have probably heard about this, and we could have an entire hours-long lecture on supersymmetry and why it's a really cool idea. But suffice it to say, if we had found some supersymmetry particles around the same place as the Higgs mass, that is, just around the corner, there's a little higher energy at 13 TeV in 2015, that would have really, really helped explain why the Higgs mass is the way it is. It's more or less what it does is it postulates, supersymmetry postulates you have all the known particles that we know exist, standard model, capital S, capital M, and you do this one spin flip thing, and you postulate a totally different, like a completely other copy of the particles that have slightly different properties. And they might have super high masses or the different masses. Obviously they'd have high masses, otherwise we would have found them already. But it basically says, there's this extra particles that in a sense can cancel out the other ones when you calculate what the Higgs boson mass is. That's, don't worry about the details, just suffice to say, if we had found some that would really, really help explain why the Higgs mass is the way it is and why we see it where it is. But we have not found any evidence of these at all. And that's weird. It's really weird. And I hope that some of you are particle physicists in the room and you can like sympathize or empathize with this. Is like, it's really strange because it would really make a lot of sense, because otherwise there's really no reason for the Higgs mass to be what it is. The mass, the Higgs mass, we don't choose this number. Nature chooses this. We go out and measure it. It's like the electron mass, or it's like the electron charge. We can't change it. We just go out and measure it. But a lot of these numbers that we see in physics, they seem to have, some of them have some relation to other numbers. It's like, oh, that makes sense because of X, Y, and Z. And oh, this makes sense because of X, Y, and Z. The Higgs boson mass doesn't seem to come from anywhere. And it's not what you would choose if you were designing a universe from scratch. It's like, yes, this makes sense. This is logical. I'm going to totally put this Higgs boson mass right in here. And that makes us start to think, if there's no supersymmetry, for example, to keep this mass in this kind of low range where we see it now, it makes us start to think in very strange ways. And it's clearly not a proof or a demonstration of the concept, but it makes us start to take more seriously the idea that maybe our Higgs boson mass is nothing special, because maybe our universe is nothing special. Maybe our Higgs boson mass is just one of an almost infinite number of possible Higgs boson masses that each one got assigned to a different, almost infinite number of universes, sampled for some probability distribution. So we know that probability distributions, we know that nature loves probability distributions, like the average resting heart rate of an adult male will go in some kind of Gaussian, right? And if you stand on a street corner, you're watching cars come by, the cars come by will follow a Poisson distribution. We know that nature loves statistical distributions. So why would nature behind the scenes not love statistical distributions too? And possibly our Higgs boson mass was one that happened to be stable, because here we are to talk about it. I mean, the Higgs boson, if you don't know and love it already, maybe there's some good books you can read, but suffice to say, if there was no Higgs boson, there would be no indication of the Higgs field, and if there was no Higgs field, atoms would never have formed, and we would never be here in this beautiful auditorium having this conversation. And so the Higgs boson mass that we have really indicates that, it's a concrete demonstration that we are here to have this discussion. Our universe is stable, but it's possible that there were an almost infinite number of other masses of the Higgs boson that led to universes where maybe they expanded a little bit and the Higgs boson mass was wrong, and maybe the electron mass was wrong too, and the alpha constant was different, and so this one never formed atoms, and all the particles just whizzed around and nothing ever happened and no structure ever formed. Or there could have been different values of different things in different universes where they expanded a little bit and then they collapsed immediately because they didn't have the right conditions. So this is an idea that we take a little bit more seriously after the lack of discovery at the LHC so far. It is not in any sense a demonstration or a proof of this idea, but it makes us start to think in new ways, and that's exciting. So that's why this kind of the lack of a discovery can really spur new ideas. But at the end of the day, we really, really like hints. We really like places, where people ideas to say, oh yeah, you should definitely look for the new discovery. It's going to be totally in this experiment over here, or oh, it's definitely going to be just around the corner in this energy range. We're kind of out of those, because the dark matter, we've been looking for it in different ways in different experiments, but it's kind of the suggestive hints as to where it should be are not playing out the way we expected them to. And the question, of course, is that we now need to think in different ways. Or so the idea is that we now need to think in different ways to, about particle physics, about physics in general. Like, where's the new discovery going to be? We don't have any more guarantees, and that is somewhat, scary. But it's also a bit of freedom. But are we really out of hints? I mean, I keep saying this. Is it really just completely out of hints? Do we have no idea where dark matter could be? Do we have no idea where supersymmetry could be? Do we have no idea where, why our universe is made out of matter and not antimatter, which is a totally different discussion, but this is another big open question of science right now. I mean, because the real question is the thing that I'm really, I'm getting to the end here, but the thing that I came here to motivate to you is that we have to build bigger colliders. And why would we build a bigger collider if there's no concrete specific prediction as to what we'll find? It's because in the past, every time we built a bigger collider, it's always worked. So go back to J.J. Thomson. In Cambridge University, Cavendish Laboratory, this was back in the days when a lone white male could completely change the world by himself on a tabletop. Those days are gone, luckily. But this is, he could actually completely discover the electron by himself in 1897. And then we went bigger. So I'm skipping through several decades, but in 1959, for example, we got up to decide there was a proton, to design a proton synchrotron of about 628 meters around. And just by contrast, so this is Thomson on a table in Cambridge. He discovered the electron. When we went to this alternating gradient synchrotron at about 800 meters in Brookhaven in the 1960s, he discovered something called the charm quark, which was a totally revolutionary discovery, made everybody take seriously this notion that quarks, those things inside the proton, were actually real and not just like an interesting bookkeeping thing. Then we went bigger. The superproton synchrotron, 7 kilometers around. In the 1970s, the W and Z bosons, those one I've referenced many times. I love the W and Z, awesome particles, and they were discovered by going to a bigger collider, because they were not within the discovery range of any of our other colliders. And in a similar size ring at the Tevatron at Fermilab was discovered the top quark. And then we go forward. The Large Hadron Collider in 2010 was turned on and eventually discovered the Higgs boson. But that's the last remaining guaranteed discovery. Remember that, the Higgs was the last thing that we were guaranteed to find. But we still have all these open questions, and we have no idea where they're going to be. We have no clue. We have suggestive hints, but the hints are running out, and they're not so well motivated anymore. So the next generation and the next generation of particle physics colliders have to go big. We have to cast a wide net, and we have to do it in some way so that we can split the difference between something that is possible within a reasonable amount of time, within reasonable budgets, things like this, and something that would really get us to large enough energy to be able to answer the questions definitively. Because the thing, just to use one example, that supersymmetry thing, it doesn't have to be within 13 TeV. It's always like there's always a bit of a rough, there's always a little bit of wiggle room with the supersymmetry thing. You'll talk to the theorists and like, oh yeah, it's definitely going to be here. Oh, it's definitely going to be here. Oh, it's definitely going to be here. It's an amorphous beast. But it should be within the range of the TeV range. But to answer the TeV range definitively, we should go really high. Let's go above the TeV range, and then that would answer the question completely. So the next generation of particle physics colliders are going to be something like the CEPC that might be 50 to 70 kilometers around in China, and maybe this would get us to the discovery, just right around the corner. And the next, another one that's being discussed right now is the Future Circular Collider, about 100 kilometers around at CERN, and both of these will maybe start taking data in the 2040s. But once again, the discovery, there's no guarantee that it's going to be right around the corner. It could be anywhere in this range. So, to really answer the question definitively, we should go big. We should build a collider around the circumference of a great circle of the moon. And this would be 11,000 kilometers around. And it would look something like this. This is an artist's rendition. And it would get us up to a high enough range in energy that would more or less be able to definitively answer the question, is supersymmetry right around the corner, or is it very unnatural? And once again, this natural thing in terms of physics, it's a little bit hard to motivate these days because naturalness as a concept is, my colleague, one of my colleagues often says, simplicity is not a principle of nature. At the end of the day, you actually, because our world is actually not so simple in certain ways. I mean, it's very Baroque. If you were some deity designer in the universe, we'd totally not design this one. It's really bizarre. The standard model is nice, but it fits together in really strange ways, and there's different values of things that are chosen. You wouldn't design this at all. And so this kind of naturalness argument is kind of going out the window. But getting up to tens of thousands of TeV would really allow us to completely definitively answer this question with respect to, is supersymmetry a natural symmetry of nature? And it would more or less make us it would spur us to think in completely new ways about how to answer this biggest open question, because we're kind of running out of ideas. We're kind of running out of ways, the best ideas as to what dark matter is, why gravity is so weak, these things. But so I can say these things, and I can put the funny, I can put the funny images up, and like, look, I drew a line on the moon. It's kind of interesting, right? But we're also adults, so it behooves us to talk a little bit about the concrete details about, designing such a thing, a hadron collider around the circumference of a great circle of the moon. So the estimated budget that I came up with, I have no idea. And of course, the timeline. Let's talk about when it's actually going to happen. You tell me. No, but what I mean by this is that this is something that is almost impossible to say. And, well, it's possible to say at the moment. If we wanted to do this right now, basically impossible. And like insane impossible, right? And insane impossible is not going to happen, right? But if I were to, and I'll give you an example of a more concrete estimate, not just a question mark. So the 0th order Moon Collider budget estimate, only for the construction of a tunnel similar to the LHC. This is 100 kilometers. 100 meters underground. And the magnet installation. So for the LHC construction, the tunnel was already there, but I factor that in as well. To say that was about $4.6 billion. Sorry for pounds and dollars. You have to do the conversions on your own. But this is $4.6 billion, and just so simply scale that up to 11,000 kilometers around the circumference of the moon. This is $1.9 trillion. We're going to need some innovation to get these costs down. So this is the place where I want to really kind of like remind you that this is not a concrete proposal for a particle collider around the circumference of the moon, but it is instead a means to spur ideas as to what we would get if we did something like this. And in fact, it's not such a crazy idea because there's a lot of threads kind of going in this direction that within, I don't want to say a couple of years, but maybe a couple of decades, it might be possible to do such a thing. And that's with the last few, I guess I'm running out of time, the last few minutes I'm going to motivate those things. And really what I'm doing is I'm kind of hoping that there might be some tech people in the audience, or maybe some startup company people, or maybe some innovators, because there are some huge innovation opportunities for a moon collider. So I'm gonna put a little chart here. What I need from you, and what you could use this for, is innovation for an industry. Because I'm a particle physics experimentalist, not a product developmentalist. I have no clue what you do with these things. As you know, with particle physics experiments like this, anytime you do something huge, anytime you go something big, there's always transferable technology. Just because you have to invent stuff. This happens all the time. That's guaranteed. This is like open-ended humanity R&D. There's always stuff that you end up transferring to. You always end up transferring to industry. So I'm going to go through a few things that I need from you. I need magnets about 10 to 100 times stronger than the LHC magnets that are about 8 Tesla, and I need 11,000 kilometers worth of them. Okay, so I think I've seen a few smiles in the audience, and not completely insane ones. Somebody I think is saying, "Ooh, I can do that," So I need reliable space transport schemes for equipment and rotating personnel. And actually, NASA's a little bit ahead of the game on this, right? They've thought about this Orion thing. There's the idea of personal space transport things. I need tunnel scouting, engineering, and digging. Okay, well, scratch that. Maybe I need self-directed and self-learning robots for tunnel scouting, digging, installation, and maintenance of the magnets. But then you think to yourself, okay, digging is slow and takes an extremely large amount of money, so maybe we don't need to go on underground. Maybe we just need to do it on the surface. Maybe what needs to be done is the calculation as to, can we get away with some surface level collider around the circumference of the moon that would still be able to withstand the constant barrage from small meteoroids coming all the time. This calculation needs to be done. So somebody in the audience needs to do this for me as well. We need LHC-style detectors, but more finely grained and general purpose to ensure sensitivity to a wide range of new particle discoveries, and automated, because we don't want to have personnel up on the moon all the time, at least not thousands of people like we do at CERN. Automated, this is for the data scientists in the room. We need automated data analysis and anomaly detection methods designed by physicists, but optimized using the cutting-edge machine learning techniques that are customized for our uniquely structured big data from particle physics collisions. We need some speedy, robust moon-to-Earth data transfer system. So some like network people, totally, this is your innovation right here. We need advancements in power, combination of nuclear, but also solar, because solar is abundant on the moon. There's no atmosphere, so you can get solar power, and it's much more efficient than it would be on the Earth. And everything else I haven't thought of yet. These are innovation opportunities. And then, so I've got the list here on the left, what I need from you, and here's some examples of what you might be able to use this for, these innovations for in industry. like I said, I don't know. You tell me. Every single one of these things would have transferable technology to be used in private industry and to be used for commercialization. And it's like, I mean, so I'm putting these things down, a little bit. I'm being a little bit playful. Clearly, I mean, I'm not saying that we're going to concretely build this thing next year or even 5 years from now. But what I am observing is that there are threads. So every single one of the things that I listed and things that I need from you, people have been thinking about this with respect to space travel and with the moon for a while now. And things have are starting to get some momentum and get some steam. And so the history is sort of like we're destined to keep doing this type of thing. Apollo 11, man walks on the moon. And once again, there's kind of like a tabletop experiment that he's doing there, on the moon. And then flash forward to things like the ISS in 2006. And people ask themselves, what are we going to do with the ISS once it's decommissioned? Could it be used for commercialization? Could the technology be used for some kind of space transfer system? SpaceX, of course, everybody knows SpaceX. It's been making great strides with private space travel. And then even NASA, back in 1977, was thinking about moon bases. Obviously, moon base has been the idea both in science fact and science fiction for a very long time. But in the current day, there are people that are really interested in doing this and going back to the moon to stay. And I don't know this guy, Bob Richards, but he and I were both at South by Southwest, or he was supposed to be at South by Southwest last week, but I didn't get a chance to see him because he wasn't there. But he says he has a company called Moon Express, and he's like, return to the moon, this time to stay. And one of the express things about like building a moon base is like, what are they going to do there? If you build a moon base, what are they going to do? Well, one thing they could do is they could be in charge of a gigantic particle collider. Right? And it's not just this Bob Richards guy. As you know, there's this Google Lunar X Prize. And if you notice down at the bottom here, this was a Google Lunar X Prize. There were like 9 teams that invested a lot of time and effort into try to make a moonshot to land on the moon from private companies to land on the moon. None of them ended up getting this prize. It was supposed to happen by this year, and they just determined that no one's going to make it to the finish line. But each one of these teams really thought deeply about it, and there's a lot of innovation already going in that direction. Let's take these threads and push them into one place and really make this happen. And so, if you think about it, the idea of like having a moon base and maybe, like I said, the people that are there, the moon base people, the astronauts that are there could be, partially particle physicists, and they could keep track of a gigantic particle collider around the circumference of the moon that could help us determine what dark matter is and why gravity is so weak. But it doesn't have to be just that. If you had a moon base, imagine what else you could do. So Vera Rubin, if you don't know who Vera Rubin is, I urge you to look her up. She's one of my heroes. The Vera Rubin Lunar Science Center, a particle collider at 30,000 TeV on a great circle around the circumference of the moon. You could also have a base that is devoted to optical astronomy that astronomers have loved, have wanted to put, have dreamed about putting observatories on the moon for a long time. You could have gravitational wave astronomy. You could have direct and indirect detection dark matter experiments. You could have precision measurements in low gravity conditions. You could have a quantum computing center. And you could have organization that is based upon the CERN and the ISS models, which we know work quite well for international or non-national collaborations. And so, at the end of it, I know that right now, many of you in this room right now are thinking the following very valid question. Isn't this absurd? I mean, why in the world would we do this when there's so much poverty and hardship and so many social problems here on Earth? The truth is that the resources exist to both solve all social problems and to devote a relatively small portion toward boundary-stretching scientific exploration like a particle collider around the circumference of the moon. But the current prevalent socioeconomic system has engendered a world and an attitude that makes us think we have to choose among things like this. The current system and the, let's be honest, relatively small number of extremely wealthy power holders who more or less exploit every single one of the rest of us has a vested interest in convincing us there's no alternative. The current system, politics makes me frustrated. But it makes us think that we have to choose between things like this, and it makes us want, it tries to convince us that there's no alternative to this system. I mean, that's really how hegemonies persist. They aggressively and unrelentingly convince you that that they're inevitable. But if I, as a scientist, can embrace new ideas, new paradigms, and not feel threatened, but celebrate when new ideas force us to change our thinking about the nature of the universe, and trust me, I guarantee you, if you come up with a new theory, one that incorporates all of our observations of elementary particles and includes dark matter and gravity and supersymmetry and all of these observations, I guarantee you I will celebrate. If I can do that, then we as a society need to remain open to the possibility that alternate, more equitable systems do exist. Ones where everyone wins, where we can eradicate poverty and we can build a particle collider around the circumference of the moon. These do exist, and that we can create them if we simply recognize their objective superiority. And even in the largest, even in the current moment, don't let anyone ever tell you that big projects like this are some kind of drain on society. Consider it in the context. This is very much in the US context, but I looked at the percentages and they're not, factor 2 or 3. It's not too different for the UK. So the LHC construction was about $8 billion, and it costs less than $1 billion per year to operate. The US Department of Energy budget is about $30 billion, and the NSF, National Science Foundation, is about $7.5 billion per year. By contrast, the contribution to the LHC that they give is about $170 million, paltry. And the NEA and the NEH, these are the arts and the humanities associations or the endowments, are minuscule and proposed to be zero by the current administration. By contrast, the US military budget is $700 billion. And for some private sector examples, Uber is currently valuated, whatever valuated means, at $68 billion, and Palantir Technologies is valuated at something like $20 billion. And if you add up all of the unicorns, these private companies that are worth over $1 billion each, then this is about $650 billion of valuation. Excuse me. If we as a society valued scientific curiosity as much as we valued allowing private companies to facilitate governmental intrusion and surveillance of their citizens around the world, undermining, aggressively deporting and targeting marginalized communities in the United States, for example. Palantir is one of the companies that has given this, the machinery of deportation to ICE. And if we valued scientific curiosity as much as we valued private companies to undermine strong service sector unions, such as those covering, taxi drivers, if we valued scientific curiosity as much as we valued these things, we could build a particle collider around the circumference of the moon and definitively explore these concepts of, dark matter, what happened just a fraction of a second after the Big Bang, and why is gravity so weak? All these things that have been keeping me up since I was a little kid at night. So this, that, and the political screed part. But what I really want, we're getting to the very end here, and I have to tell you, the entire talk here has more or less been a lie. I don't really want a particle collider around the circumference of the moon. I want something more. So I said that about 30,000 TeV would be pretty great. That would allow us to really answer some questions. That's still not exactly what I want. I want 10 to the power 16 TeV, because that's something called the Planck scale, and I urge you to look up the Planck scale. But basically, it's the place at which gravity and quantum mechanics, quantum world, governs all the particles that we know exist and the ways they interact, and it works really, really well, the standard model. And gravity, the thing that doesn't play well with it at all. But this is the point at which they have to have something to do with each other. It's impossible for them not to. And this would be 10 to the power 16 TeV. And it's not such a big deal, because to get to there, all we need to do is build an LHC-style collider around the orbit of Neptune. So maybe that's not going to happen anytime soon. But it's also probably not going to happen with our civilization. So this is the sort of thing that I would call insane impossible, because it's clearly not going to happen. But the concept of a moon collider, a particle collider around the circumference of the moon, I would classify that currently as just kind of regular impossible. And impossible is getting to the point where it's getting, because of these threads I was saying, people are interested in going back to the moon, advances in robotics, interested in, the Boring Company, these types of things. People are interested in going back to space and really maybe putting a moon base and really doing some science, in thinking in new ways. These threads are all going in the direction where the regular impossible could, this actually could be a regular impossible concept. And regular impossible we can do. I mean, impossible is just impossible just up until the moment when it becomes possible. And, it almost seems inevitable in a sense, because for a kind of curious sort of primate species like we are, either staring up at the sky from a hot flat rock in southern Utah, wondering, stargazing, wondering about the vastness of space, or gathering together the best, most curious, most inventive parts of humanity from all, across all racial, national, religious, barriers to come together in places like CERN, or, for example, to build a particle collider around the circumference of the moon. This is what we do. This is what our species does. We're curious about the universe. We want to know more. We're not satisfied with particle physics. You get into particle physics if you're the sort of person as a kid, you were never satisfied with the answer because I said so. When someone says, when you ask why. It's like you want to know the answer, you keep going forward. And this is really what we end up doing. And so you might, even if we were to build a particle collider around the circumference of the moon, this would, let's say we were able to find all these particles. We find a dark matter particle. We find extra forces of nature. We find supersymmetry. Hurrah, everything is explained the way we kind of expected it to. Even if we didn't find anything at a moon collider, that would teach us a lot. That would more or less definitively, demonstrate that our universe is a bit strange. Not definitively. It would definitely point us in the direction that our universe seems a little bit odd, and it would make us start to think more seriously about this concept of the multiverse. And at that point, somebody may come up with a way to really test that idea, because the multiverse theory is just an idea until somebody comes up with a way to definitively test it. So a null result, the lack of a discovery, can be just as instructive as a discovery. Because in particle physics, there's no such thing as failure. The only failure is to stop searching. Thank you.